Yes,
Shall I on the video, sir?
yeah, yeah, no issue. We are just starting the streaming. Okay. Yeah, good afternoon, everyone. This is the third session of day 5. It's the last session of this FDP. Uh, we have with us Mr. Akshay Mastood. Now, presently, he is serving as design consultant and mentor at Polar UAE LLC, United Arab Emirates. He has more than 5 years of industrial and academic experience. He is MTech with specialization in automotive technology from COEP Pune and ARAI. He is co-founder of COEP Sunrisers Research Lab, which design and developed electric vehicle. He is also a co-founder of Cortex Enterprises. Organization deals in product designing and 3D printing services. So this was a brief introduction of Mr. Akshay Mastood. I would request him to take over the session and start with his technical talk.
Thank you very much, sir. And first of all, very warm welcome to all of you. Okay. And after that, obviously, I have to say good afternoon, respected faculties, researchers, and other delegates. Okay. I would like to thank you, FCRIT, to give me a wonderful opportunity to speak in ATL FDP session. Now, now, in this session, okay. In this session, we will discuss very crisp and very broad design and development of solar electrical vehicle. That is actually we design and develop at our COP Sunriser Research Lab. Our vehicle is designed with respect to very specific constraint and set parameter given by Imperial Society of Innovative Engineer for Electric Solar Vehicle Championship. One more thing I want to add here, I would like to say that this is complete vehicle. These all vehicles are a collective efforts of many people such as engineering students, industrial and researcher. So so in the current slide, if you observe, there are four till now our research lab developed vehicles, four versions of the electric solar vehicle having it shows the different character, it shows the different specifications. Okay. In the today's session we'll discuss about the version 1. Okay. And obviously these are the some specification of all versions of the vehicle that was developed by our lab. Okay, this is our lab. Okay, let me tell you one thing about our lab. This complete lab is about 500 plus square feet, consist of many many system or many systems or many devices instruments. Okay, and we have the very good space here for the project like this. Okay. So these are the glimpse of some version 1 vehicle. Okay, so these are the some pictures. Okay, so today we'll discuss about this particular vehicle through like this. Okay, solar electric vehicle, obviously it is divided into two kinds of the system. First one, it is the mechanical. First one, it is mechanical system, and second one is a electrical electronic system. Now mechanical system consists of chassis, steering system, braking, suspension, transmission, body. An electrical electronic system consists of motor, its controller, battery and BMS, solar panel and MPPT, sensor and switches, wire harness. If I divide it in a rough manner, I can say almost in the throughout the vehicle, almost 45% consist of mechanical system and almost 55% consist of electrical and electronic system. Okay. Now, in this particular presentation, my skeleton of presentation is something like that. First, we'll discuss about design calculation part in a very broad manner, in a very generalized fashion manner. We'll discuss, because we don't have the so much of the time, right? So we'll, in a very generalized manner, we'll discuss design calculation part. After that, second part, if any CAD model is there regarding any system, I will show you some pictures of that CAD model. And actual third actual implementation of that particular system or that particular part in the vehicle. Okay, actual implementation. Okay, so in this fashion, the whole systems or individual system I divided. Okay, before the start of this project, I will the first step comes in a picture, that is nothing but what, understand the whole rules, regulation, norms, as well as some parameter, design parameter given by the Imperial Society of Innovative Engineers. And as per the plan, as per the rules regulation, we develop some layout so that understand the whole system completely, you know, understand which part is placed at where, connections between each part. Okay, and so that this particular layout is very important to plan our project development stages. Okay, so in this particular system layout, if you observe, it is started from the main part of this whole layout. Obviously it's an electric vehicle, so it's a motor, I can say. Now this motor, it is connected to the battery with the help of some control circuit. Okay, which control circuit, and obviously this battery, it is connected to the solar panel with the help of voltage stabilizer, later on we called as MPPT here. Okay, so obviously solar panel is charges the battery. Okay, this is one charging method. Second charging method is, it is nothing but what, through the AC supply, through the AC supply. Okay, if now this motor, it is connected to the wheel, rear wheel of the vehicle, rear wheel of the vehicle. Okay, with the help of transmission, or in most of the electric vehicle, it does not require any kind of the transmission. We'll discuss this particular part later on. After that, this is particular is nothing but what, steering system. Okay, this is the dashboard on which we have the control panel, you can say. Okay, all control panels, such as it controls the headlight, as well as the brake indicators, ignitions, switches, battery indicator. Obviously this is the battery indicator, charging indicators. All these things are placed on this control panel. After that, obviously this represent the wheels, those who are unaware about this particular thing. That is, these are the four tire or wheel, you can say. These are the wheels. Blue color part is nothing but what, suspension. Whatever the dotted parts are there, these are the connections. These are the connection, electrical connection or wiring harness, in generalized wiring harness, you can say. Okay, and after that, we have here brake system, accelerator or paddles, we can say, accelerator and brake paddle. Okay, so this is nothing but what, generalized layout of electric solar vehicle, specifically for this particular project. Okay, so one by one, we'll discuss in shortly, we will discuss, rather I can say. Okay, the first mechanical system is chassis. Now this is the design methodology what we follow. Now in chassis, there are many designs are available, like body on frame chassis, okay, unibody or monocoque kind of system, monocoque chassis I can say, roll cage, tubular space frame, okay. But specifically we select the cost point of view, design point of view, and the time constraint point of view. We select our chassis as a roll cage or tubular space, you can say. Okay, now first in this design methodology, the first step is make a rough sketches. Okay, see, gentlemen, uh, we follow all the things like this only. Okay, we follow all the steps. Okay, and let me tell you, we took around out of 7 months of project, we around take 4 months for just for the design part. Okay, so literally we started from the scratch. Okay, so this is a thing that what I want to mention at this point. Okay, so this design methodology of the chassis, the first step is the rough sketches. You have to make some, you have to make some rough sketches for your chassis by the on the basis of your research, or by the on the basis of your understanding about the component. So you have to make the rough sketches of the chassis. After the second stage, that is nothing but what, you have to make the CAD model. Okay, you have to make the CAD model. In We use the CATIA as our software tool, CATIA V5. After that, whatever you made, whatever you design the CAD model, you have to, those people who don't understand the CAD means computer aided drafting. I hope there are some faculty or people who don't know about this term. CAD means computer aided design. That is a 3D so 3D uh, uh, 3D structure, or you can say a 3D virtual structure, you can make it. Okay, and this CATIA is a software tool through which you can develop this CAD model. Okay, after that, by the process of there are many process through which we have to follow, and after that we have to do the crash analysis in ANSYS or Hypermesh. These are the software tools through which you can understand, or you can understand, or you will analyze your model by doing the stress analysis, deflection analysis, and other many tools. Okay, after that, if in the crash analysis, we'll discuss all this thing. I will show you the pictures, guys. uh, in the crash analysis, is somehow any component is failed, any component is weak. Okay, crash analysis means simply when, when vehicle is crash, because of that what happened, any component, any part get failed. I mean, it will literally, it will crack. Okay, so in generalized word I want to say, if in the crash analysis, if the CAD model what we design in CATIA is failed, again you have to redesign that model. Okay, redesign that model, and again you have to follow the same procedure as in the crash analysis. Okay, and after the crash analysis, if your model is ready, then you will make your prototype here, prototype here. Okay, prototype is a pre-manufacturing stage, I can say here, as per my experience. Here you can understand, understand two things through the whatever we design, whatever is design is correctly implemented here, correctly implemented it here. And second thing, whatever the things we miss, that what we have to implement it in actual vehicle. Okay, and apart from that, other suggestion, design point of view, actual manufacturing point of view, here at this stage you can discuss. Okay, after confirming all the things, you can come to the final stage, that is as per the suggestion, uh, as per the modification, we can again redesign all the CAD all the model, and again we follow the same thing here. Okay, so as per we follow this design methodology, we in this to design this particular vehicle, we almost follow 7 to 8 models. Okay, so we design this particular this is the final model, chassis model we design in CAD, we design in CATIA. Okay, so this is called as roll case chassis. Okay, and we follow some design consideration. Obviously I will there are many actually, but for this time, for this point of time, we'll discuss 3 4 here. Okay, the first one, that is the weight of the chassis, that it should be low as possible. Second one, that is nothing but what, the driver egress of 5 seconds, means what, in case of accident, if we want to if in case of accident, that is damage of battery or uh, any kind of the problem regarding the vehicle, electrical, electronic or mechanical failure, driver can easily access through this, easily exit from this vehicle within a 5 seconds. Third is nothing but what, the driver should have the vision of 200 degrees and 100 degrees on other side. Suppose this is the driver position, so driver can easily view, he had the vision of almost 3 to if this is a center of line, I can say, so almost 100 degrees from this side, 100 degrees from this side. Okay, so this is the criteria of the vision. Okay, and obviously fourth point is nothing but what, driver comfort. These are the our parameter what we develop or what we reach in this particular development process of vehicle. Okay, so maximum length of our vehicle is 1500 mm, maximum width is this, height is this. Okay, pipe OD is this. Pipe means what, this is a tubular structure, so obviously this is in general a word we called as pipe here. Pipe OD is 25.4, thickness is 1.2 mm, and one important part is material, that is what we select a material for AISI 1018. Now this material is very good for machinability point of view, machinability point of view. Okay, and obviously it is cost effective too, that what I have to mention here. So these are the nothing but what other views of our vehicle. This is front view, side view and the top view. See, this is the first step, that is nothing but what, development of CAD model. After the understanding of the placement of the components, suggestions, advices regarding the design point of view, manufacturing point of view. Okay, after the CAD development of the CAD model, we have to go for the all these tests in a softwares like ANSYS you can use or Hypermesh you can use. Okay, so in this, these are the tests what we have to follow. I will show you directly the test samples of some crash analysis, so you will get to know exactly what I have to mean. Okay, so these are the tests what we have to follow to understand the which are the weak component in the particular system. Okay, with respect to some set constraint parameters. Okay, so there are some tests we have to follow. So if you observe carefully, this red color, blue color part is nothing but what, it is safe. Okay, now when I supposed to safe means what, there are some values are given, the range of the values through which you can understand this particular component. This particular component means, when I say component means this is the component, this is the component. Okay, or this is a part of the chassis you can assume. Okay, so when I say it is safe, that means it shows it have the very less stress at this particular with respect to the parameters which is used in the ANSYS software. Okay, so these are the safe. Okay, the blue color shows it's and comes under the safe region, and the red, it shows it comes under the weak region. Okay, so I have to redesign. Okay, and redesign. Okay, in case of, so I can say in case of deflection, maybe here this particular component is fail. It just with this particular conditions are apply, means we will get the result as per the set parameter. So these are the other tests like a side impact test, okay, bending test, torsional test. So from this we can conclude that you know by considering some other factors too, we conclude that whatever we are develop the chassis is fine for this particular championship, or for this particular when we when we drive the vehicle the on the track, I can say. So this particular vehicle is fine, okay, or this particular chassis design is fine, so it passes all the tests, okay. And how we can say it is accept, how we can say this particular chassis is acceptable or not, it based on the value, we'll get it, value of the stress, value of the deflections, value of the force through this test, front impact test, side impact test, bending test, torsional test, and the pump test, okay. So through this we can understand, through these values we can understand the our vehicle, it is safe or it is a acceptable design, the chassis is a acceptable design, chassis design is a acceptable design, okay. So obviously this particular value should come under the acceptable range, okay, so that we can say the chassis is in a acceptable range. So this is just a picture, after development of chassis, this is our methodology, this is our prototype development stage. We use the plastic pipes so that we can figure it out, okay, this is the position, this is the brake position, this is the accelerator position, okay, this is the vision of for the driver, okay, this is the battery, this is the battery position, okay, this is the control panel position, this is the solar panel position, okay, this is the MPPT position. So we just very much sure through this prototype development, okay, this is and everyone can easily visualize, okay, what we have to develop, when we have to develop, and where we have to put the particular component or the system at what place, okay. So this is the stage through which we were very conform, okay, conform. And after that we make our the first chassis like this, okay. So this is the chassis, so that you can, after the prototype we finally make our chassis, okay. So weight is almost, if you I literally measure the weight of this particular chassis, this weight is almost 16 to 17 kgs, like this, 16 to 17 kgs, okay. So this is a chassis finally, okay. After the chassis, the first after the chassis uh, after the chassis, the next systems comes in a picture, that is a steering system, right. So in a steering system, obviously there are this is rack and pinion type of steering. It generally widely used in conventional vehicles, but our to with respect to our vehicle constraints, we use the lever arm steering with bell crank, okay. Since there are other factors like weight, we want it should be, the weight of the steering should be very low. Second is that obviously cost of manufacturing. Third is very important, that response of the steering system should be very fast. And in this vehicle we use 1:1 turning ratio, 1:1 turning ratio. That means with the help of, if you just steer 1 degree, if you just steer the 1 degree, okay, the the tires will change its direction from the 1 degree. So that's the reason I call it is as a, we develop 1:1 turning ratio. But here effort requirement, steering effort requirement is quite high compared to conventional vehicle, okay. Now, this kind of the steering is very useful in case of the cornering, because we have to, we have to drive this vehicle on the racetrack for the endurance round. Okay, so we keep this particular point in our mind. Okay, now to coming back to the design of the steering system, we have the certain parameter we have to consider. Okay, that is the wheelbase, wheel track, and crash caster camber and kingpin inclination. Okay, so these are the basic parameter we have to develop, so that you will get a geometric steering geometric calculations. Okay, steering geometry calculations, obviously this is we develop all the calculations, uh, I mean according to calculation we make the geometry in the CATIA. So this is a basic understanding with respect to mathematical point of view, design point of view, you can say where exactly the steering will come. Okay, and apart from that we have the other calculations too, so that we'll get to know the forces requirement, efforts requirement, okay, to drive the vehicle. Okay, so this is called as steering rod here, you can say, and this is nothing but what, tie rod. Okay, this is the ball joint, and I will show you diagram. Okay, how it is implemented. So this is the steering system. Okay, so this is the steering wheel, obviously this is the steering wheel, this is the steering rod, and this is the tie rod. Okay, now this is connected to the knuckle. Okay, this is the knuckle, means what, it is connect knuckle, this is a part which is connected to the wheel. Okay, your suspension system and your steering system, so that you can control the vehicle by with respect to direction point of view. Okay, with respect to direction, see somehow it is look like this. Okay, so when you steer at 1 degree or 5 degree, obviously this particular vehicle take a turn of 5 degrees or whatever it may be. So my meaning, initially I told you, that is our turning ratio is 1:1. See, as this is our first vehicle, so we have to make our system very easy. Okay, very easy from manufacturing point of view and design point of view, that what I would like to mention here. Okay, and on steering wheel we have some controls like indicators, the horn, you can say. Okay, after that the next system we comes in a picture, that is the braking system. So this is a very important system in any vehicle basically. Okay, and this is the one of the very much on the priority basis, we have to develop, we have to give the calculations, and we have to design this braking system, because it the safety of when you are driving the vehicle, the safety, it is with respect to this braking system. Okay, so main requirement of the braking should be is nothing but what, braking force distributed simultaneously or distributed evenly, you can say. And vehicle, first requirement is that braking force should be distributed properly on each wheel. Okay, depends on your design. Okay, which type of the vehicle and what are the condition. Okay, so braking force distributed simultaneously, first requirement. Second, vehicle should stop within the set limit. Okay, this is the second requirement. Now coming back to our design, we have the two independent reservoir, which is connected to the master cylinder. Reservoir means what, we fill obviously the oil, because this is a nothing but what, it's a hydraulic braking system, right? Now hydraulic braking system, right? So we fill the oil here, I will show you. We'll fill the oil, and through this master cylinder the pressurized oil, it is supplied to the disc brake. I will show you here, supplied to the disc brake. Okay, Okay. So my point is that now we use two independent reservoir, Why? Because during the test or endurance, if any reservoir is failed, at least one should be operational. So that's the purpose. Okay, that's the purpose of this particular independent reservoir. Okay. Now here in this system, what happened when you apply the brake? Now this is the brake pedal here. When you apply the brake, pressurized oil, it is supplied through this channel like this. Okay, like this, like this, like this. Okay, like this. Okay, and now this braking obviously depends on the driver's efforts and what kind of the system you use. Depends on that. The stopping distance is, you know, within a stopping distance it will stop. So when you apply the force here, pressurized oil is supplied through this reservoir and through this channel, and it will approaches to the near to this particular display. Okay, I'll show you here. Okay, so this is our CAD model. So this is the reservoir, you can say. This is the master cylinder. Okay, this is the accelerator. Sorry, this is the brake pedal and this is the accelerator basically. Okay, so this is the brake pedal and this is the accelerator pedal. Okay, so somehow it will look like this. Okay, and these are the input data. These are the input data required for the braking. So input data required for the braking system. Generally, I like to say, I like to say here, in the front, we required a more brake force. Why? Generally, people, you know, assume that we have to apply the front brake very smoothly. Okay, that is acceptable. But the thing is that in actual sense, we required, as per design point of view, we required more brake force in the front. Why? Because in particular in when the vehicle in a straight motion. Why? Because in a straight motion, when a vehicle is in a straight motion, more weight is transferred to the front side. Okay, more weight is transferred to the front side. So that is the reason we required a more brake force on the front side. You observe in a two-wheelers also, generally in a front we have the disc brake, and back or rear wheel we have the drum brake. Okay, you can easily observe this thing in two-wheelers also. Okay, okay, so these are the data. Okay, and we use the formula here. Obviously the period of very short, so we can't discuss all the formulas required to develop the braking system, right? So basically these are the inputs, and through this I will say these are the output. That is, our stopping distance is almost 13 meter and braking time is almost 1.95 seconds. Okay, this is quietly high, but with respect to this vehicle and our constraint, this is fine. Okay, now we did the thermal analysis of the thermal analysis of this disk. Actually we use this, okay, but for the comparison point of view, we did the thermal analysis of the disk like this also. This is the ventilated disk what we use in our vehicle. I will show you. Okay, so this is nothing but what? Braking system. This is the reservoir. See, at the manufacturing point of view, I told you in design, in design there are two reservoirs, but if you observe carefully, we use only one because there are some constraint comes, like we will not get the we actually we manufacture two reservoir, but one of the reservoir is failed, and we have the very short time also and fund also. What I'm So So that's the reason we decided to use only one reservoir. But this one reservoir, it is operational for the front, operational for the braking regarding the front wheel. Okay, regarding the front wheel here. Okay, and the rear wheel, it is nothing but what we use the drum brake with the hub motor. We'll discuss that particular point. Okay, so this is nothing but what braking system. Now here braking system, I would like to add one more point here. See, before braking, actual implementation of braking, we have to do some, we have to follow some procedure. Okay, because there are some bubbles are present here. Bubbles are present here, and we have to remove that bubbles by the process called as bleeding. So in the bleeding process, you have to open all the pipes here. You have to open all the pipes, and you have to put the oil. We use the dot 3 oil. This is a grade of this oil, dot 3 oil. We fill the oil, and we follow the bleeding process here, through which whatever the bubbles are there, because if the bubbles are present in the particular pipe, what happen, it loses the control in, or I can say it is not much effective braking, will not get any much more effective braking efficiency. Okay, so this is the thing. So we have to remove all this, okay, bubbles, and the process is called as bleeding process. Okay, now next mechanical system, I hope the people are not sleeping here. Okay, and the next mechanical system, it is nothing but what, suspension system. So in a suspension system, obviously the first requirement regarding the suspension system is nothing but what, wheel should be always connected or contact with a road surface, any road surface. It should be, this is the first requirement of the suspension system. And second requirement, or secondary requirement, I can say, that is the comfort. Okay, first requirement is that it should be always connected with the road surface in any situation. This is the first requirement. Okay, and second is, obviously all know, that is the comfort with respect to, you know, potholes or bumps, anything. Okay, now suspension plays very important role in vehicle design, right? For example, if I say, you know, the Ferrari or the Rolls-Royce, the Ferrari have very quite stiff suspension, and comparatively stiff suspension, and Rolls have comparatively soft suspension. Okay, because this suspension plays very important role while cornering. Okay, and in the cornering, with respect to Ferrari, let's discuss with respect to Ferrari. So at cornering, the Ferrari achieve this corner at very high speed also, if the suspension is stiff, comparatively stiff. Okay, but it is not in case of Rolls-Royce. In case of Rolls-Royce, at cornering, uh, uh, it's not, you know, it will not give the such kind of the stability, such kind of the stability what you get it in a Ferrari. Okay, while cornering. Okay, at a high speed. So obviously in Rolls-Royce, we have to use the comparatively the soft stiffness or soft suspension for the comfort. Okay, in our vehicle we use the coming back, I mean, in our vehicle we use the little bit stiff suspension. Okay, because there are so many, you know, corners are there, and we our when we drive the vehicle, that the speed of the vehicle is almost 45 to 48 kilometer per hour. Okay, now coming back to the design of the suspension system, these are the parameters, essential parameters. I put it here. I'm not put any kind of the calculations here, but these are the generalized inputs Okay, that is the CG, center of gravity, vehicle load, weight distribution. That is very important. Okay, that is very important. According to that, you have to set your the stiffness of the spring, I can say, track width, camber, caster. Okay, so these are the input parameters. If you have any doubts regarding what is the caster, camber, okay, so you can just mail it, or you guys are very smart, you can just google it and you will get the all information. Okay, here we will discuss just what we use as our input data. Okay, apart from that, in generalized word, if I want to describe the design input data required for the designing of the suspension system, these are the input data. The sprung unsprung mass means what? Sprung mass means what? This mass. And unsprung mass means what? This mass, this kind of the mass. Okay, spring data, tire data, what kind of the material you use. Okay, all these things we required. Now this particular data, all this data is with respect to we have to use in the software. We use the Lotus software here. Okay, so in the Lotus software, we actually will get we actually design the system like this on the basis of all these parameter, and these are the mathematical values of all these parameter. Okay, now in this software we have to put all the input data. Second, we have to define the joint. Okay, after that the system it simulate the steering, bumping and cornering condition, and we will get the data on the graph. Okay, on the basis of these parameter, and after that, with if the parameters comes under the within certain acceptable range, then we'll go for the manufacturing. Okay, this is the thing, this particular parameter is acceptable, now we'll go for the manufacturing. Okay, obviously we develop some CAD model here. Okay, so this is nothing but what the CAD model, okay, of the suspension. Okay, so in okay, so this is the front spring suspension, this is the front suspension system, and this is the rear. Okay, and I told you initially that suspension system is connected to the knuckle, so we designed the knuckle as per our requirement, and we did the analysis. Okay, on the basis of the steering, bump and cornering. Okay, now analysis means what? We have to check from which portion of this particular part is going to be failed. Okay, okay, so obviously the red part shows here we have the maximum force. Okay, so obviously I can say this particular portion of this part going to fail. Okay, this is the thing. Okay, so before applying the suspension system, we have to set the wheels as per our design. So for that we uh, we build this particular kind of the fixtures, and okay, we achieve our caster camber with the help of small software we use. For that you will get the idea about the angles, right? Angles means what? The caster, camber, all these things we will get to know. Okay, so as per our design, we set all these parameter and we fix the wheel like this. After that we fix this suspension. Now which kind of the suspension we use? We use wishbone type of suspension. There are many types, like MacPherson is there, wishbone is there. So we use here the wishbone kind of the suspension. So how it looks? It look like this. Okay, so we set the wheel. Okay, we set the wheel, we put the knuckle. Okay, now this is purely, it is made up of aluminium. Okay, and this is designed by our team members itself. Okay, so it is purely made from aluminum and in a complete one block, from the one complete block. Okay, so this is the aluminum, this is the wishbone type suspension, this is the spring basically. Now one end of the spring, it is connected to the chassis, and another end of the end of the suspension spring, it is connected to the knuckle. Okay, knuckle okay, so this is nothing but what? Suspension system. Okay, this is the this MacPherson we use front side, I mean at a front side. Okay, like this in this picture you can easily observe. Okay, at a front side we use MacPherson type of suspension. You can easily observe here also. Okay, so this is the MacPherson, and at real we use the normal suspension. Okay, normal suspension with the swing arm. Okay, this is called a swing arm. I'll show you where we use the swing arm, where we use the suspension. I will show you here. Okay, so after implementing I mean designing all mechanical component. Okay, so we have to analyze. Okay, we are we are confirmed. Okay, this is our system. Okay, so in this system you can easily observe whatever we design. Okay, whatever we design or whatever we implemented in this particular vehicle, these are the nothing but what? All components. Like we started with the chassis. This is the chassis. After that the steering system, after that the suspension system. We use MacPherson, wishbone, and here this with a swing arm we use this suspension here at the rear. Okay, now if you observe carefully, our vehicle in the front we have the two tires, and at the rear we have the one tire. This kind of the type of this type of the vehicle, it is called as tadpole based design, or this kind of the design you can say tadpole based design. Okay, now this design is very good regarding the, as per our study, as per our research, we find that this particular design is very good while on when we drive the vehicle on a racetrack. Okay, so finally this is the model what we get. Okay, okay, so this is nothing but this is the CAD model, and this is the actual implementation of all the parts. Okay, actual implementation of the all the part. Okay, here we are going to understand this particular rear wheel. That is nothing but what? It's a hub BLDC motor. Okay, but before proceeding we'll just discuss those who are just come in between the session. So for them I just revise in a very short period of time. Okay, so this is the chassis we actually implemented. After that, this is the suspension system, steering system. Obviously here it is not mentioned, but obviously there. Okay, suspension system. Okay, this is the rear suspension. Okay, the tires, and if you observe carefully here or here, this is the disc brake. Okay, so sorry, this is a disc, and we did the analysis for the disc. Okay, thermal analysis or the disc. Okay, so this is the vehicle. Now coming back to this particular system, that is nothing but what? Hub motor or transmission you can say. Okay, the hub motor or motor we can say. Okay, see, regarding the motor or transmission, in generally there is now this is my belief. Okay, so in general there is no separate transmission is required in electrical vehicle as required in a conventional vehicle. Transmission means what you are operating, like gears, manual or automatic gears like this. So in case of but there are, I can say, in case of electrical vehicle, we use transmission called as reducer gear we use. Okay, we'll discuss this thing. Okay, but let me tell you, there are 2 3 commercial electrical vehicles are there in the market. They have their own transmission system right now to control the speed and the torque of the vehicle. Okay, but in our vehicle we don't have such kind of, I mean, in a version 1 we don't have the such kind of the transmission system. Obviously, for other than other versions, we have our own transmission system what we design in our lab. Okay, but in this particular kind of vehicle, we don't have any kind of the transmission system. We use the reducers here. We use the controller. Okay, now in this our vehicle we have the fixed transmission. We use the fixed transmission system, and for that we follow some methodology for the selection of motor. Because of some reasons we can't manufacture the motor, but definitely in our third vehicle we manufacture our own motor. Okay, with respect to our set parameters. Okay, so we follow the methodology for the selection of the motor regarding with respect to this vehicle. Okay, so we have to find out the torque at each wheel. Okay, design constraint by the rule book. Okay, so design constraint is that maximum you can use the power of the motor up to 2 kilowatt. Okay, operational voltage is about 48 volt. You can use PMDC or BLDC motor, and the motor should be drive as as a rear side, from the rear side itself. Okay, so these are the some parameters. Okay, on the basis of these parameters and other load factors, okay, in dynamic load factor also and static load factor also. So we studied the different types of the motor. Okay, what is the suitable for our vehicle as per our vehicle and the constraints. Okay, and after that we come to conclusion we have to use 2 kilowatt of BLDC hub motor. Okay, we controller. Now this particular kind of we initially, as this is the first time we are developing electric vehicles, so we don't have our own controller, but the following models they have their own controller. Okay, so this particular first controller and motor, it is sponsored by the Hero Electric, sponsored by the Hero Electric. Okay, now this is the BLDC hub motor, how it look like this. Okay, now this whole system, okay, it is the sponsor, I mean only this system, not the tire. Okay, only this system, it is sponsored by the Hero Electric vehicles, Hero Electric. Okay, and this is the hub motor with a drum brake. Okay, with a drum brake. Okay, so this is the hub, and these are the parameters. Okay, all the specifications of the hub motor, that is operational voltage is 48, power rating is 1500 watt, rated speed is 600 rpm. Okay, so these are the motor. Now with respect to with respect to, you can say, actual load condition, we almost get around 42-43 kilometers per hour. Now this is with respect to design. Okay, so we'll get 45 kilometer per hour, but on actual field we will get around 40-41 kilometer per hour. Okay, now here we mounted the motor at the rear side. I told you how it mounted here. Okay, and for that we have to, obviously we have to follow the wiring harness to control the vehicle speed, or we have to do all the wirings to control the motor. Now this is the motor controller. It is connected to motor at the rear. It is connected the motor at the rear, and it is connected to the paddle. Okay, it is connected to the brake accelerator basically, right? Now so when you press the accelerator paddle, obviously some with the help of this controller, motor controller. Okay, this is the controller, I can say, and this is the motor. Or motor means what? You can say it is a rear wheel, because this is nothing but what we call as hub motor, like this. Okay, so this is the hub motor. Okay, hub motor means what? The wheel and the motor, it is at a same point. Okay, so this is the hub motor. Okay, this one. Okay, here it is the motor. Okay, so when you press the paddle, obviously with the help of controller, it regulates its speed, and we control the vehicle. I told you that we use the initially I told you we in this vehicle we didn't use the transmission system like what we use in a conventional vehicles, right? So here we use the reducer gear system. That means why? Because the motor speed, it is very high. It is very high with respect to conventional vehicle speed. Okay, so obviously we are controlling the motor speed from high to low and in between. Okay, with the help of this controller. So we use the reducer gear transmission here. Okay, other than that, in general, in commercial vehicles also, they don't use, generally they don't use the transmission. Okay, as like a conventional vehicle. Okay, but in our next versions of the vehicle, we use our own transmission system. We design our own transmission system, and we successfully implemented the own transmission system. And here in this vehicle, there is, in this particular kind of the vehicle, there is small drawback that it will not, it will not reverse back. Okay, it will not reverse. I mean, we don't have the reverse facility in this particular kind of the vehicle, but in our successive vehicles we have the both, like forward also, obviously forward also and reverse also we can successfully implement it. Okay, now coming back to the battery system. Oh, I forgot one point here, that is the wiring harness here. Now here we use the wiring I mean, we use the high voltage automotive grade wire. Okay, now why we use the high voltage automotive grade wire? With respect to, obviously it carries only for particular parts, like battery to motor, motor to solar panel to again battery, and other controller like accelerator. Okay, for in this particular system we use the high voltage automotive grade wires. And uh, mm, for other accessories like ignition switch, horn, or light, or indicators, right? Ignition switch, like other controllers here like horn, okay, or indicators. So we use this auxiliary battery of 12 volt. Okay, so for that we use low voltage batteries. Okay, a low voltage, what you call the automotive grade wires. Okay, in general, in the vehicles, the operational voltage is around 48 to 300 volt. So our system is definitely, if you observe carefully, this system is work for the 48 voltage. For that, we use the automotive grade of wires. Okay, and wiring system means what? Here I will show you small things. That is, now this is the motor. Motor is connected to the controller. Okay, motor is connected to the controller. Okay, controller, and controller is connected to the battery, here, and also it is connected to the accelerator paddle here. Okay, battery, it is also connected to the solar panel. Okay, solar panel, I will write it in very short. Solar panel, it is sorry, battery is connected to MPPT here, some small voltage stabilizer it is used here. We use the MPPT. We'll discuss what is mean by MPPT. MPPT we use. Okay, and this MPPT, it is also connected to the motor. Okay, through which I mean, from the solar panel, in case of discharge of battery, we can use the solar energy to drive the vehicle. Okay, and we use here, now this is with respect to traction battery. Okay, okay, the all the things are operated by the battery here, traction battery. And for the auxiliary kind of accessories, we use the separate battery of 12 volt here. Okay, which you know, through which we can control the indicators. Okay, indicators, and the indicators, ignition switch, battery indicate. The indicators means what? Brake indicators, I want to say, brake indicators, or the headlights. Okay, and one more indicators, like a battery indicator, battery charging indicator, right? All these things we implemented here. Okay, in this wire harness, there is one more very important element, that is nothing but what? Kill switch. This is called as kill switch. Okay, now this kill switch plays very important role in case of any kind of, you know, uh, mm, any kind of the accident regarding the electrical point of view. Okay, that is, you know, bursting of battery, or high voltage, high current uh, draw or leakage current. In that case, if you are not controlling, somehow you are not controlling the vehicle, so you have to press that particular kill switch. He can, here you can also observe, here also we have the kill switch here at the corner. Okay, so that driver can easily you know, push this particular kill switch. Okay, and he will stop the vehicle in case of the emergency, in case of the electrical failure, what according to you know, he feel, if you know, he don't have any control on the track. And I will mention here, you know, this thing is happen on the track when we drive the vehicle at on the track at both. Uh, this thing is happened. One, what happened is that in between the endurance round, somehow some electrical failure come, and our vehicle gets stopped. Okay, and uh, and some kind of, you know, short circuit occurs basically. So we'll get to know that some short circuit is happen, and the vehicle gets stopped. Okay, so what we did, obviously this kill switch is connected in between the supply, battery supply, and the accelerator. So we find out our this guy, actually this is the hero of that particular scenario. His name is Sudesh. He find out the mistake problem, and he just on the point, I mean, just he used the presence of time, and he just, you know, remove this kill switch, and he directly connected to the connected to the controller. That is it is connected from accelerator to controller. Okay, apart from that, other than, we have the two kill switch, three kill switch we have. One is here. Okay, I will show you the position of the kill switch. One is here, one is here, one is at the back, here. So we have the three kill switches. Okay, for the safety of the vehicle in case of the emergencies. Okay, so these are the position of the kill switches. Okay, now next thing we have to discuss, that is the battery. Now we have a certain operational voltage, that is nothing but a 48 voltage. Okay, now in this battery, with BMS, which what? Battery management system, which control the uh, which control the battery in the operational conditions. Okay, that is the temperature or bursting and all this thing, or high voltage, high current supply. So all these things, it is controlled by the this BMS, what is called as battery management system. It's work as a controller. Okay. Now the thing is that how we select the battery, because uh, uh, how we select the battery, this is the question. Okay. Now depends on our this is the depends on our conditions, like what kind of the drive what you have to follow on the track. Okay, so this is a track, this is the actual rpm go-karting track at Bhopal. Okay, so this is a track on which we drive our vehicle. Okay, if you observe carefully, so many turns are there. Okay, and on this track, we have to run the vehicle for the endurance round, and we decided that in the endurance round our heavy acceleration is about 3 minutes, mild acceleration is about 22 minutes, and cruise, that means the constant speed acceleration, is about 65 minutes. So total endurance time is 90 minutes here, right? About 1.5 hours you can say. And operational voltage is 48 volt, right? This is very important. So those who are interested, they can, observe this thing. Okay, that's what we followed basically. And the current required for the heavy acceleration is about 40. So actually we measure this current in this condition in case of heavy acceleration. Obviously this is a no load condition. Okay, 40 amperes, 40 amps. And in case of mild acceleration, when you drive the vehicle for the 22 minutes, in case of mild acceleration, the current requirement is 30 amps. In case of cruise, you drive the vehicle for 65 minutes, the current required is around this 22 minutes. Okay, and if you follow the energy formula, that is nothing but a VIT by 60. So you will get an energy in kilowatt hour. Okay, or watt hour basically. Okay, so we multiply the time, voltage and current, so you will get an energy for heavy acceleration. Similarly, for mild acceleration, if you multiply all these parameter, you will get the energy for mild acceleration. And in case of cruise also, you will get a energy. Actually I'm not calculated here, but in case of cruise, you will also get a energy. Now you have to add all the energy here, so you will get, this is the energy 1794. Okay, and obviously you have to follow the Ohm's law, and you have to follow the this power formula, that is P is equal to VI. Okay, through which you have to use energy is equal to VI. Okay, so through which you already you get the energy here, that is 1794. Operational voltage, that is a 48 volt, and you can find out the current capacity required. So obviously through which you will get around 37 amperes hour. So this is the current capacity required. After that, if you consider the 20% safety margins and the current for the other accessories too. Okay, current for other accessories too, so you will get around 46 ampere hour. And considering 80% of the efficiency, that is the 20% of the loss, you can say, you will get the 57.9. okay, so how you get for 57 80, you have to 46.6, you will get it from the 20% from this, from this safety margin you have to consider. And here you will get a 57 ampere from this Okay. And after that you will get to know, okay, this is the current capacity required, maximum current capacity is required as per the load. Okay, as per this condition, as per this condition, maximum current capacity is around 58, you can say around 58 you will get. Okay, and considering all safety margin, efficiency, you will get 50 amps. Okay, 50 amperes. Okay, so so that we find out. Okay, see, on the basis of this parameter also you can manage to develop your manufacture or develop your own battery pack system. Okay, but I told you, because of the shortage of the fund and the time, we search nearby the battery around this particular capacity. So about it is 60, about on this nearby rating we'll get a this particular battery, that is 65 ampere hours, 48 voltage. Okay, based on our survey and the calculation. Okay, so 65, when I say 65 ampere hours of battery, and each hour, suppose we use 20 ampere hours of ampere hours of battery energy, we'll find out we drive the vehicle around 3 hours. Okay, so okay, we find that the vehicle will run with respect to these parameters. Okay, what we calculated, vehicle will run around 3 hours. Okay, but let me tell you one thing here, this is with respect to theoretical calculation. In actual field, this is something, I mean, there are some other factors also we have to consider. Okay, like the load of the vehicle, load of the dynamic load of the vehicle, right, and how the driver is driving the vehicle. Okay, cornering, when the vehicle is on follow the straight line, vehicle runs vehicle will driving on the curves. So all these parameter we have to consider. So obviously these 3 hours it will reduce down to around, let's say around 2 hours, you can say. Okay, so we'll get to know our vehicle will run for a 2 hours with a maximum consideration. Okay, and obviously charging time it is required, it is around 7 to 8 hours. Okay, it is not exactly 7 hours, but it will take more than that. Okay, we use here lithium ion battery as the we in conventional vehicle, generally we get to know that we already know that there are lead acid batteries are used. Okay, but here we use the lithium ion battery, what we call Leon batteries, na, lithium ion, which is used in batteries, computer, laptops, everywhere. Okay, so this is a battery pack. Okay, and for the control we design our own BMS here. Okay, so this is the placement of the battery at the rear. Okay, this is the battery placement here. Okay, so in between battery and driver we put here shield also, I will show you at the end. Okay, at the, so this is the battery, it is connected here. Now the battery, it is again, it is connected to driver and other parts of the system. Okay, if you observe here, these are the nothing but what, electrification of the vehicle. I think we already discussed all this wiring harness here. Okay, now the this is the you know this is the last part of this system, electrical system, that is solar panel with MPPT. Right now, so in the market also we have the several options for the solar panels. Okay, see, you can design your old solar panels also, no problem. But I'll tell you this thing is that The manufacturing solar panel is quite difficult process, complicated process. Okay, although we tried at a second version, we tried flexible solar. We tried to manufacture one cell of the flexible solar panel in our research lab. Okay, but it is very complicated, and so many things we have to follow there. So okay, so at this time, we have the option to select our solar panel as per our requirement. So basically in market, we have three kinds of the solar panel. The first one is called amorphous silicon solar panel, or also called as thin film. Okay. Second is nothing but our polycrystalline. And third one is monocrystalline. Now amorphous having the efficiency around 7 to 10%. Okay, polycrystalline it around the efficiency 12 to 15%. I hope all you know aware about this efficiencies. Okay, 12 to 15%, and monocrystalline it is around 18 to 20%. Okay, 18 to 20%. Recently I get to know that there are other types of solar panels are there, what we called as CPC, that is the concentrated photovoltaic cell, CPC. That efficiency is around 41% approximately, if I'm not wrong. 41% approximately. Okay, now in our vehicle system, in our vehicle, in design of our vehicle, we have to use the solar panel for the two purposes. First purpose is that to charge the battery. Second purpose is that to run the motor. Okay, to run the motor on by taking the power from directly from the solar panel. So these are the two purposes. Okay, and how we calculated, how we decided which kind of the solar panel we have to use, or which power capacity of the solar panel we have to use. That is on the basis of some characteristics. Okay, on the basis of our load on the battery, charging capacity of the battery, the capacity specifications of the battery, what kind of which type of how much energy is required to run the motor, that is that capacity, and other parameters like this operational voltage. Okay, operational voltage and all. Okay, on the basis of that, we calculated the design, we calculated the capacity of the solar panel what we required. Okay, and we will get to know we required almost 185 of watt, because in how the standard standard solar panel is around this particular watt. Okay, so anyhow we have to use this particular solar panel having the capacity of this particular watt. Okay, so on the basis of the calculation load requirement, we decided the solar panel having this kind of the electrical characteristics. In this, the short circuit voltage, open circuit voltage are the very important characteristic, and after that the maximum efficiency. Okay, maximum efficiency at all operational temperatures. All these things are very important. Now basically we calculated all the things correctly, but the thing is that this when we select the solar panel, we have only the options of polycrystalline initially. Okay, at initially, because this calculator is quite suitable for the polycrystalline having the efficiency of 12 to 15%. But since the solar panel, now this is the a advantage of the solar panel, you can say the space. Okay, it will take so much of the space. Okay, so with respect to polycrystalline, with respect to 185 watt of energy, The solar panel is very huge, you know, in size. Okay, so almost to achieve the 450 watt of energy, 454 kilowatt of energy, or let's say 3 kilowatt in anyhow, let's say consider 3 kilowatt of energy, we have to use the 3 panels of the polycrystalline. Okay, so it is quite difficult to manage, so we search for the another option. See, we are discussing here with respect to actual manufacturing point of view and whatever the condition what we face at the time, that what I'm discussing here. So we try to find out the another option, and uh, luckily we get a monocrystalline panel having the same capacity as what we initially implemented, try to implement it with the 3 panels. Means whatever we are getting the energy when we use the 3 panels. Okay, same energy will get it from just uh, one solar panel, one monocrystalline solar panel. Okay, and obviously this particular solar panel also sponsored by one of the company called Ecozone. So they are the technological partner in our vehicle. Okay, so after that, according to the solar panel specification of the solar panel and the specification of the batteries, we design our own MPPT like this with the help of Eagle software. See, honestly speaking, I'm from the mechanical background. Okay, and one of our team members or group of a team, they design this MPPT on this Eagle software what they use there. Okay, we just my role is that okay, this system is successfully workable or not, that what I have to understand, I have to take care of that thing. Okay, now this is the this is the MPPT. Okay, now guys, MPPT, why I use the MPPT, like MPPT, those who are not aware of MPPT, for them I want to give a short brief on the MPPT. So MPPT works like a voltage stabilizer. Okay, MPPT's full form is maximum power point tracking. Okay, now MPPT is a such kind of the device, you can say, such kind of the device is you can say it it includes it controls the power in such a way that it extract the maximum available power from the solar panel PV module, you can say, under the certain conditions. Okay, now the voltage and the voltage, the voltage at which the PV module can produce the maximum power, basically it is called as maximum power point or max peak voltage, peak power voltage. Okay, and depends on various conditions such as solar radiations, the temperature, ambient temperature, and the solar cell temperature. This particular power get varies. So here the MPPT work. Okay, so MPPT try to figure out all these things. Okay, and it will uh, uh, according to requirement. Okay, it will collect all the powers, okay, from the solar panel. Okay, and it will supply to the, this is the MPPT, this is the solar panel, this is the MPPT. Okay, and according to requirement, it will supply it will convert into maximum power. Okay, so the major principle, you can say, MPPT is nothing but what, extract the whatever the available power from the PV module by making them the operate at the most efficient voltage. most efficient voltage, and with the help of MPPT we'll get all the things here. Okay, so basically MPPT works as a voltage stabilizer. We will get the energy. So finally, this is the CAD model. It is implemented electrical electronic system also, like solar panel, battery here you can say, and this is the final model. Okay, this is the final model. Okay, now after that we tested our vehicle. I will show you here. This is a testing video after implementing all the mechanical electric electronic system. We have to test the vehicle. So somehow we tested like on the campus, at the campus. Okay, and this is the vehicle. Okay, complete vehicle. And this is just a glimpse. I want to show it here of SCV 2.0. For this vehicle, we get the sponsorship from the Siemens itself, around 3.5x. Now in this vehicle, if you observe carefully, we use the flexible solar panel. Now this type of the vehicle is quite different. It is a two-seater, multi-seater you can say. And initially our vehicle was the single seater. Okay. The first vehicle was on, it is a three-wheeler. This is the four. Okay. So these are the some pictures, like this. Just it's the end of this particular slide, so I want to end it like this. So we win the championship, we participate at just the first year of the participation, we win this. This is the second. Almost we'll get best design, runner up, innovative technology, all these things we use. In this vehicle they also use a water testing also, waterproof testing. This is the third vehicle. Thank you guys. So I want to end my presentation. If you guys have any doubts, you can mail me, no problem. Thank you. Hello.
Yes, Mr. Akshay.
Yes.
Shall we take
Thank
questions?
You, sir. Yeah, sure, sir.
Yeah, participants can either raise hand or post in the chat box.
How I know?
No, I will tell you the questions. Yeah, I think there are no questions at present. Nobody has raised the hand and there is no chat box message. So I think we'll conclude the session because immediately after this we are having a valedictory session.
Yes, I understand,
so,
sir.
yes, Mr. Akshay Mastood, thank you very much for coming over here, sharing your experience, sharing your knowledge, and
thank you, sir.
Addressing the audience over here. So definitely looking forward to meeting you in future. So on behalf of Mechanical Department, Father Rodrigues Institute of Technology, thank you once again.
Thank you, sir. Thank you, sir. One thing I just want to, at the end, I want to mention, I just represent this particular whole project as a representation, but this is the collective efforts of all team members. That what I want to mention here at this point of time. Thank you. Thank
That's
you, sir.
true. That's true. Yes. Yeah.
Thank you, sir.
Okay. Bye. Yeah.
Thank you, sir.
I request all the participants. Uh, Now we'll be going into the validatory session and the test. So everything I will be telling over there. So just join the next meeting in the calendar, which is the validatory session. I'll give 5 minutes more so that we can disconnect from here. Take 5 more minutes. We'll be starting at 4:10, and it is in the next meeting. Please don't join this meeting again. The validatory link is there in the calendar section. So we'll join over there, and further discussion will be taking place over there. So thank you all very much. I'm ending this meeting. Bye.